Uh-oh. Hello. Am I up and running? I can't tell. Good morning. Wait for a few more people to show up.
No. No.
Waiting for a few more people.
No.
Hello. Okay, I'm at 15. I think I'm going to get started. So hello everyone. So today is going to be sort of our last lesson on data analysis, and so we're focusing today on graphing. Okay, so you already learned how to propagate uncertainties for things that are multiplied together, things that are added together, etc. Okay, and so now we're going to learn about graphing. So and how do uncertainties fit into graphing? Okay, and so really the idea is, if I say, let's say that y equals, okay, let's say 4 plus or minus 1, that means that y is between 4 plus 1, which is 5, and 4 minus 1, which is 3. Okay? So what if I have, and then what if I have an uncertain value of x, which is maybe 2 plus or minus 0.5. All right. Then that means that x is somewhere between 2.5 and 1.5. And we talked about how it doesn't mean that that doesn't mean that it's 100% within this range. It means that it's about 66%, 2/3 of the time it's going to, the likelihood, the probability is about 66%, with certain assumptions about how the uncertainty is working. Okay? So anyways, what if we want to plot x comma y? Okay? if we wanted to plot x comma y, so we have our axes, let's say, 1, 2, 3, 4, 5, 6, 7, and then here I'll go 1, 2, 3, 4. Okay, so here's our axes. So if we plot our point, we're going to plot x comma y at our best guess. Okay, so our best guess is that it's 2 comma 4. All right, so 2 comma 4 would be right here. All right, so that's my best guess for where this measurement is. However, okay, we know that y could be between 5 and 3. All right, so what we're going to draw is what is called an error bar that is a graphical representation of the uncertainty. So I know that my y value could go up as far as 5, and it could be as low as 3. Okay, so I'll put little lines there, and I'll connect them with a TIE fighter. Kind of looks like a TIE fighter to me. So this is called the error bar. So obviously the more uncertain a point is, the taller its error bar is. All right, so this is a really uncertain point. This is a point that is not as uncertain. All right, so this is the you can have vertical error bars, and you can have horizontal error bars. So the horizontal error bar goes from 1.5 to 2.5. So it goes from here to here. And so we have a horizontal error bar as well. Notice how these error bars appear the same size, but really it's like comparing apples and oranges because they have different scales on the axes. And also these are representing different quantities. So maybe x is measured in kilograms and y is measured in meters. I don't know. So this horizontal error bar represents an uncertainty of 0.5 kilograms, and this vertical error bar represents an uncertainty of 1 meter. So the actual size of these so basically what I'm trying to say is don't compare the size of a horizontal error bar to a vertical error bar, okay? Because they're comparing apples and oranges, all right? So basically what you're doing is you're creating a, just kind of like a box. You're saying the data point is probably within this box, okay? All right. Oftentimes, the uncertainty is negligible in one direction. So, maybe the uncertainty in x is negligible. If the uncertainty in x is negligible, then we would just draw the data point like this with only a vertical error bar. If the uncertainty in y is negligible, then I would draw it with just a horizontal error bar. Okay? So, error bars, these are important. All right, so it gives you some idea of, how uncertain your data is in a pictorial way. All right, so that's the first part of this lesson. The second part is what types of relationships are common in physics. So if you know what types of relationships between x and y are you likely to see? Okay, and so let's talk about some of them. Okay, one type of relationship is called a linear relationship. Okay, so a linear relationship is one where our sort of model equation, okay, is y equals ax plus b. Okay, so we have our graph of y and x, and it looks like a straight line. Okay, a and b are called free parameters. Okay, so a and b can be whatever numbers, and it still qualifies as a linear relationship. So as you know, a would represent the slope and b would represent the intercept. So, changing a and b changes the slope, changes the intercept, shifts it up and down. But no matter what a and b are, it's still a linear relationship. Okay? So this particular graph that I've drawn has a negative value for a and a positive value for b. All right? So you should be able to kind of hang on a second. I just realized something. You should be able to look at a graph and kind of guess what is the relationship. All right. Okay, so another type of relationship is called a proportional relationship. So proportional is similar to a linear relationship. Okay, it's a linear relationship where the y-intercept is 0. That's called a proportional relationship. So y equals ax. That's a proportional relationship. So all proportional relationships are linear relationships. Linear relationships are not necessarily proportional relationships because this is not proportional because the y-intercept is a positive number. Okay? So this is the model equation. The free parameter is the slope. Okay? Now, another type of relationship that is very common is called a power law. So a power law is one that has a model equation of the form y equals a times x to the b power. Okay? Now, so what does this look like? How do you identify it? Well, so here's y, here's x. Have you ever seen a graph of y equals x squared? I think you probably have seen a graph of y equals x squared. And it kind of looks like a parabola. Okay? So that's basically what it looks like. It starts at the origin because 0 to the any power is just going to be 0, right? So it starts at the origin and it's kind of bendy, all right? So this would be a b that is greater than 0, okay? Of course, b could also be equal to 0.5, in which case it looks like a square root graph. So So, it's something that starts in the origin and is bendy, all right? So this is a positive. This is actually a b greater than 1, okay? What does it look like if you have a b value that is, what if you have a b value that is greater than 0 but less than 1? That's going to be something that looks like a square root graph. So maybe something that looks like this. All right. Another thing you have to consider is, a power law. Okay. What if you have a power law with a negative b? So have you ever seen a graph of negative b is kind of like y equals 1 over x? That's x to the negative 1 power. So that graph kind of looks like this. So it kind of comes down from infinity and then flattens out. Okay. So again, this is y equals ax to the b, but b is negative. Okay. All right. So that's a power law. So you should be able to look at some data and be like, I think this is maybe a power law with a b value that is, negative. Or I think this is a linear relationship with a slope that's negative and a positive intercept. Okay. So another relationship that you should be able to identify is an exponential relationship. Okay. So the model equation for an exponential relationship is y equals a e to the bx. Okay. And so exponential growth kind of looks like this. A couple things about exponential growth is it does not start at 0. If you look at exponential, so this is b greater than 0. Okay, this is called exponential growth. How can we tell the difference between exponential growth, for example, and a power law? Oops. A power law with b greater than 1. Well, yeah, it is. It's tricky to tell the difference, but one way you could tell the difference is that the power law starts at the origin. Exponential growth does not start at the origin because anything to the 0 power is 1. Okay. The other difference is that exponential growth is always increases faster than a power law. Okay. So an exponential growth overtakes a power law eventually. It might not at first, but it always does eventually. So this is exponential growth, which has b greater than 0. But you could also have exponential decay. Exponential decay is when your b value is less than 0. Okay? And so exponential decay kind of looks like this. All right? Now, what is the difference between, you can see that exponential decay looks a lot like, it looks a lot like a power law with b less than 0. Okay? But a power law actually goes up to infinity. All right? It has a vertical asymptote, whereas exponential decay has a finite value. at x equals 0. All right. Some other things. You can shift power laws, power and exponential laws by a constant. Okay? You can shift power laws and exponential laws by a constant. So that would be, for example, y equals ax to the b plus c. So if you have a function f of x and you add a constant to it, it shifts the graph up and down. Okay? So that would take this graph, for example, and make it look like this. And you can do the same thing with exponential. Okay? And again, that shifts the graph up and down. So you should kind of be able to just look at a graph and kind of guess. Is it power law? Is it exponential? Is it a shifted exponential? Is it linear? Is it proportional? Just take a guess. It doesn't matter if it's the right guess necessarily, but you want to try to figure out what is the relationship between the variables. Okay? All right. So I'm going to show you how this works. Okay, so I've got Desmos pulled up, and I got some data. All right, so I have a data table which you can type into Desmos. So I have y1 and x1, and so I'm going to graph y1, and I've got some data here. Okay. Now you can see I have a third column in my data table, and this represents the uncertainty, the size of the uncertainty. So for example, the uncertainty, and this is the uncertainty in y. So I'm saying I have a negligible x uncertainty. All right. So basically by saying that the uncertainty is 0.7, I'm saying that this value of y is probably between 7.2 and 5.8. All right. So there's a trick. Okay. There's a trick for doing this, for putting the error bars into Desmos, which is right here. Okay. So that trick is you say x equals, and then we know that the error bar extends from my best guess minus the uncertainty to my best guess plus the uncertainty. So you can see that I have the y value for my error bar is between the minimum possible value and the maximum possible value. So I'm graphing a line x equals y between these two values, and then I say colon x1. So if I graph that, so if that doesn't make sense to you, you can just screenshot that, or because for your IA you're going to have to make graphs such as these. Okay, so I'm going to make a video that's called how to do data for your IA. All right, so you can see that once I graph that, I have some error bars. All right, so I am going to let you guys type into the chat. Actually, I'm going to go back to here. Look at that for a second, and then look at the different relationships that we learned about. Okay, and tell me, what do you think is the relationship between these between y and x. If you had to take a guess, what is the relationship between y and x? Okay, and I'm going to wait. I'm going to look at the chat and see what you guys think. So some people think exponential decay. No one thinks linear? Could be a power law with a negative exponent. All right. All right. So my main question is it's a little bit ambiguous. Okay. It's a little bit ambiguous what this relationship is. So how do we figure out what do we think the relationship is? How do we tell? Because I intentionally chose this data because it is a little bit ambiguous. So how can we go through and actually figure out what is the best relationship between these variables? Okay. So it turns out that Desmos can actually do curves of best fit. So let's suppose I think this is a linear relationship. So what I'm going to do is I'm going to say y1. If I want Desmos to do a curve of best fit, you do y1 squiggle a times x1 to the b, or plus b. All right? And so here's what we can see. All right? So that's a linear, if we tried to fit our data with a linear model, okay, it gives an r squared value. So there's kind of two ways you can evaluate this, all right? You can look at your r squared value, okay? So I can see that my r squared is 0.8988. So that's the r squared for the linear fit, okay? R squareds that are closer to 1 are better. The other thing we can look at is we can look at how far away are my data points from the line of best fit, okay? And I can see I've got a number of data points that are quite far away from the line of best fit. Now, what qualifies as being far away? Being far away means that it is more than one error bar away from the line of best fit, okay? So you can see that there are 1, 2, 3, 4, 5, 6, 7, 8 points. And only 1, 2, 3, 4 of them actually touch. Only 4 error bars touch the line of best fit. So 4 out of 8 touch the line of best fit. All right. You can see also that it gives me the A value and the B value that best fits the data. Okay. Let's try a power law. All right. So A times x1 to the B. All right. And we can see that, well, if it was a power law, if it was a power law, then it would obviously be a negative B value because it slopes downward. But you can see that we have a finite value for at x equals 0. But remember, a power law that has a negative power has a vertical asymptote, okay? So the curve fitting just doesn't know what to do. That's why it's giving this horizontal line. What we could do is maybe it's a shifted horizontally power law. All right. There's all kinds of little tricks you can do to try and make your data fit. So maybe it's x1 minus c to the b power. So that works pretty well. All right. So if I do, do you guys remember that if you do f of x minus 5, for example, it shifts the graph horizontally. If you do y equals f of x plus c, it shifts it vertically. If you do y equals f of the quantity x minus c, it shifts it horizontally. So I've shifted the power law horizontally by putting in this horizontal shift. And that actually fits really well. So it has an r squared value of 0.9917. Okay. And I can see it looks like all of the error bars are touching the graph except for one, except for this point right here. All right. So that gets 7 out of 8 error bars are hitting. So that's pretty good. Now, what is the downside of this? Well, if I look at the downside of this, the linear model only had 2 free parameters. Okay. This shifted power law has 3 free parameters. It has A, B, and C. So generally, more free parameters is a more complicated model of the data. Okay, so you want as simple a model of the data as possible. All right, so to have 3 parameters, it fits the data better, but it just it has more free parameters, so it's a more complicated model. So that's a bad thing. All right, let's try exponential decay. A times e to the b times x1. All right. So what do we see here? We've got an r squared value of 0.9914 for the exponential. The exponential model has 2 free parameters. Okay. It has only A and B. That's the only wiggle room. And we can see that about, looks like 7 out of 8 error bars are touching the line of best fit. So this has 7 out of 8. All right. One other thing I wanted to, I'm just going to do a really ridiculous curve of best fit. Okay. So what if I did A times x1. So this is going to be a really stupid curve of best fit. Okay. Let's say A plus B times x1 plus C times x1 squared plus D times x1 cubed, okay, plus E times x1 to the 4th. Ooh, it didn't like that. Plus ooh, maybe it can't handle more than 4 parameters. Plus, oh, I know what it's doing. I'm going to make that F. Okay. It thinks E is the number 2. Oh my gosh. Why did I do that? Where did it go? Oh no. Can I undo? Okay. That's a bummer. All right, well, let's just go back to here. All right. My computer is like frozen right now. Can you, hello? I've overloaded my computer. Okay, so okay, so okay, so I wrote down the data for each of these models that we tried. Okay, so the linear model had the worst R squared, and it hit the fewest, the smallest number of error bars touched the line of best fit. So that basically means this one is out. It's not a linear model. If we look at the shifted power law versus the exponential, they both have the same number of error bars touching the line of best fit. They have almost exactly the same R squared, not quite, but this one has 3 parameters, this one has 2 parameters. So probably if it were me who was making a judgment, so your human judgment comes in, what do you think is the relationship? It could be a shifted power law. So I'll just put a question mark there. But I would say more likely it is the exponential model. Okay. More likely it is the exponential model, just because that is a simpler model. Okay. What I would advise you to do is, so we're just analyzing data in a vacuum. Okay, we don't have any other information about what is actually going on. But if you knew a little bit about the physics that produced this graph, you would have a reason to believe maybe it's a power law or maybe it's an exponential. Okay, so if you have 2 models that are really close, you try to think about the physics. Okay, do the physics themselves, does the physics suggest one or the other? And then I would go with that one as my model. Okay, so for example, in kinematics, we haven't had anything e to the x in kinematics. So if this was data from kinematics, I would probably go with the shifted power law, because we have 1/2 at squared. We have power laws in kinematics. Okay, so even though this is a more complicated model, I would still go with the shifted power law if this was data coming from kinematics. If this was data coming from radioactive decay, okay, power laws are not present in radioactive decay. There's exponential decay all over the place. So I would go with exponential. You see what I'm saying? Now, the best R squared of all, before everything froze, was the polynomial model. That went through 8 out of 8 error bars, had an R squared that was even higher than this one. It was basically 1. All right? But here's the thing. You never want to use polynomial models for your data. A plus bx plus cx squared plus dx cubed plus, okay? Because they have many free parameters, okay? Polynomial models will always fit your data if you have enough free parameters. And in fact, because I had 8 data points, if I had 8 free parameters, I could make that polynomial match my data exactly. It would go through every single data point, spot on. All right? But the thing is that you have no reason to expect that the best fit for your data is going to be some random polynomial. Okay? Nature very rarely produces random polynomials as the best fit, okay? So my point in talking about this is that some random polynomial with 10 free parameters is always going to match your data better than anything else. But because it has so many free parameters, it doesn't really come from physics, okay? If you had 100 data points and you've got a curve of best fit with 100 free parameters, you're going to be able to make it match perfectly no matter what. Okay? So you never want to use a polynomial model. You can always make it look really good with a polynomial model, but it doesn't make sense physically. Okay? So I know that when you write your IA, you're going to have to do an experiment, collect the data, and decide what the relationship is. Someone is going to choose a polynomial model with 5 free parameters and say, I figured it out. I understand. It happens every year, and that person always gets a bad grade on their IA. So do not use a polynomial model, please. So that was just a little introduction of how to use Desmos to get a curve of best fit. Okay. So now one thing that Desmos does not do, okay, is because the data itself is uncertain, okay, because the data itself is uncertain, for example, the slope of a line is uncertain. So the free parameters themselves are uncertain because they're being used to fit uncertain data. Okay? So what if I have a graph, for example, y versus x? Okay? And here's some points. All right? Maybe I'll do 4 of them. Okay? And, oh, by the way, when I wrote this, when I put that data, it came from y equals 6e to the negative 0.2x. That was what the function actually was. But then I added random numbers to it to sort of make it look like it was real experimental data. Okay. So what if you have a linear relationship? What if you have a linear relationship? You can draw what is called the best fit line, the line of best fit. All right, so let me draw a line of best fit. So it's really useful to have a straight edge when you draw your line of best fit. So let me draw my line of best fit here. Boom. So there's my line of best fit. One thing about IB is even if the data is obviously curved, they still call it a line of best fit, okay? But this data is linear, okay? So the line of best fit is an actual line, all right? So that's my line of best fit. So let's say that my line of best fit, I draw this line. Now, by the way, how do you get the line of best fit? The line of best fit should go below. It should have an equal number of points above the line and below the line, if possible. And it should go through all of the error bars. It should touch all the error bars. Okay? So maybe this is, maybe this is y equals, let's say 3.1x plus 2.2, something like that. So I just randomly made up a line of best fit. You can also draw what is called a max line. So the max line is the steepest line that you could say matches your data, okay? And so the max line goes from the bottom of your leftmost error bar to the top of your rightmost error bar, okay? So this is called your, quote, max line. And what we can see about the max line is it has a bigger slope, okay? So let's say you found the equation of your max line, all right? So maybe your max line is y equals, it has a slightly bigger slope, so maybe y equals 3.5x. And we can see that the intercept is actually smaller, okay? So maybe it's plus 1.0, something like that. I'm just making up the numbers. So if you were actually doing this calculation, you would find the equation of the line. There's what's called a min line, which is okay. So here's the min line. It's the minimum possible, smallest possible slope that's consistent with your data. It goes from the top of the leftmost error bar to the bottom of the rightmost error bar. So maybe this one is y equals 3.8x plus, and we can see that its intercept is slightly higher. So maybe it's plus 2.5, something like that. All right. So if you want to know what is the uncertainty in the slope, what is the uncertainty in slope, you can approximate it using max and min lines. It's approximately going to be equal to the maximum slope minus the minimum slope divided by 2. Okay, so what is the maximum slope in this case? The maximum slope was 3.8. The minimum slope was, oh, did I goof here? The min has to be less than 3.1, doesn't it? I kind of goofed. Why did I say 3.8? I'm not sure. So this should have been something like maybe 2.9. Let's just say 2.9. So my maximum slope was 3.5. My minimum slope was 2.9. And then I divide that by 2. And that gives me 0.6 divided by 2, which is 0.3. So if I want to quote my slope, Well, my best guess at the slope is 3.1. And the uncertainty is the maximum slope minus the minimum slope over 2. So my slope is 3.1 plus or minus 0.3. So you're saying that I think the slope is 3.1, and it's most likely between 3.4 and 2.8. All right? So that's how you do that. And the same thing works for your uncertainty in intercept. Your uncertainty in intercept is approximately, now there's mathematics to get the uncertainty in slope and intercept exactly, but it's beyond the scope of this course. So this is just approximate, but IB wants you to know it, so I teach it to you. You take your maximum intercept minus your minimum intercept divided by 2. So what is our maximum intercept? Well, we have 3 intercepts here. The biggest one was 2.5. The smallest one was 1.0. All right. Divided by 2. That gives us 1.5 divided by 2. It's 0.75. So if I wanted to quote my intercept, I would say, well, my best guess at the intercept, which comes from the line of best fit, is 2.2. And my uncertainty is 0.75, which I'm going to round to one significant digit, so plus or minus 0.8. All right? So this is how you get, so let's review here. The fact that your data is uncertain means that your curve of best fit is also uncertain, which means the slope and the intercept are uncertain. So we've talked about how to get the uncertainty in the slope and the uncertainty in the intercept. And it comes from drawing these max and min lines and then using these formulas to take the slope and the intercept from those max and min lines and get the uncertainty from that. It's only approximate analysis. And furthermore, this analysis, IB would only expect you to do this for a linear relationship. All right? Only for a linear relationship. Okay? So, that is my lesson, and I will see you in the Zoom room.